All right, let's talk about the difference between code that just works and code that's built to last. We're diving into the solid principles, which are basically the architectural blueprints for writing amazing software. Think of them as the foundation for building code that's strong, scalable, and easy to work with. Let's get into it.
So, have you ever had that feeling? You're looking at your code and you're almost afraid to touch it. You know that one tiny little change could send the whole thing tumbling down. It's a stressful place to be, right?
Well, that feeling has a name. It's the sign of tightly coupled code. It's what we call a code smell, a hint that something deeper is wrong. It means everything is so tangled up and dependent on everything else that you can't change one piece without breaking 5 others. It's brittle, it's unpredictable, and it's a total nightmare to maintain.
But there's a better way, and that's where the solid principles come in. They are the industry standard solution to this whole mess. As Code with Arian puts it, they really are the foundation for writing code that you and your entire team can actually maintain, scale, and, understand without pulling your hair out.
So here's our game plan for today. We're going to start by really understanding that house of cards problem. Then we'll introduce the solid blueprint. We'll walk through each of the 5 principles one by one, and then we'll wrap up with 3 more golden rules that really tie it all together.
So let's really dig in here. How does a project that starts with the best intentions end up as that fragile house of cards? It all comes down to the sneaky dangers of tightly coupled code.
And, the really nasty thing about fragile code is how all these problems just snowball. Because your code is hard to maintain, it's also a pain to test because you can't test anything on its own. That mess leads to code that's almost impossible to read because the logic is just spaghetti, and the end result? You can't scale. Adding a simple new feature feels like performing open-heart surgery. It's risky, it's complicated, and it's slow.
Okay, enough doom and gloom. Let's talk about the solution. If fragile code is a house of cards, then solid is your blueprint for building a skyscraper, something strong, well-organized, and designed to reach for the sky.
So what exactly is solid? Well, it's an acronym. Each letter stands for one of 5 key design principles, made famous by the legendary Robert C. Martin. You probably know him as Uncle Bob. Now, these aren't super rigid laws. Think of them more like professional guidelines that help steer us towards writing much, much better code.
First up, we've got the S in solid. This is the single responsibility principle, and I like to boil it down to a simple mantra: one job, one class.
The official definition is actually super elegant. A class should have only one reason to change. What does that mean? It means every class you write should be responsible for just one single part of your application's functionality. It should do one thing, and it should do that one thing really, really well.
And this example makes it so clear. On the left, you've got this bread baker class that's a total jack of all trades. It bakes, it manages inventory, it serves customers. It's doing way too much. If your inventory rules change, you have to edit the class. If your customer service script changes, you also have to edit the same class. It has too many reasons to change. The solution on the right is beautiful. You break it down. Now you have a baker, an inventory manager, and a customer service class. Each one has a single job. So much cleaner.
Okay, next up are O and L, the open-close principle and the Liskov substitution principle. I like to group these two because they're both about a really critical idea. How do you add new stuff to your code without breaking all the old stuff that already works?
The open/closed principle sounds a little tricky, but it's simple. Your code should be open for extension, meaning you can add new functionality to it, but it should be closed for modification, meaning you shouldn't have to change existing, working, tested code just to add that new feature. Let's look at the classic area calculator example. On the left, the calculator has a big, ugly if-else statement. To add a new shape, like a triangle, you have to crack open that core class and add another else if. That is super risky. The solution? On the right, we create a generic shape interface. The calculator just knows how to work with any shape. Now, if you want to add a triangle, you just create a new triangle class that follows the shape rules. You never have to touch the original calculator. It's open for extension, but closed for modification. It's brilliant.
All right, now for the L, the Liskov substitution principle. I know it sounds super academic, but trust me, the idea behind it is pretty straightforward. It just means that any child class should be a perfect substitute for its parent class. A square class has to be able to do everything a generic shape class can do, without causing any weird side effects.
And I absolutely love this quote because it just nails the idea of LSP. A toy duck that needs batteries isn't a real substitute for a living, breathing duck. It breaks the fundamental contract of what it means to be a duck. And the exact same thing happens in our code when we get our abstractions wrong.
So here's a code example of that. Let's say we create a weird no-shape class, and it technically implements our shape interface. But when you call its area method, it just throws an error. Well, that violates the Liskov substitution principle. Our area calculator expects any shape to give back an area. This no shape breaks that promise and breaks the contract, and our whole program would crash. It's not a valid substitute. Let's wrap up the solid principles with the last two, I and D. Both of these are all about creating smarter, more flexible connections between your code modules, which is the key to making things easy to manage and test.
The interface segregation principle is all about fighting fat interfaces. The core idea is simple. A class shouldn't be forced to implement a bunch of methods it doesn't even use. It's way better to have lots of small, specific interfaces than one giant do-it-all interface.
And this printer example makes it perfectly clear. The problem on the left is that we have one huge machine interface with methods for printing, scanning, and faxing. So what happens when you have a simple, basic printer? It's forced to have scan and fax methods that do nothing. The solution is to segregate or split up the interface. We create an iPrinter, an iScanner, and an iFax. Now our basic printer only has to implement the one interface it actually cares about. And a fancy all-in-one printer, it can implement all three. Way cleaner.
And finally, the D, the dependency inversion principle. Now this one kind of flips your brain upside down a little bit. It says that your high-level, important business logic shouldn't depend on nitty-gritty, low-level details. Instead, both of them should depend on abstractions, like interfaces.
Let's see it in action. In the problem scenario, our order service is directly tied to a specific class, the email notifier. If tomorrow your boss says, hey, let's switch to SMS notifications, you have to go in and physically change the order service code. That's tight coupling. The solution is to invert that dependency. Now, the order service only knows about a generic iNotification service interface. We can then give it, or inject, any class that fulfills that contract, whether it's an email notifier or an SMS notifier, without ever touching the order service. This is a total game changer for flexibility and testing.
Okay, so we've made it through Solid. Now let's just quickly touch on 3 more principles that are like best buddies with Solid. They all work together to help you write simpler, cleaner, and more maintainable code.
Let's run through these real quick. First, we have dry. Don't repeat yourself. Pretty simple, right? If you find yourself copying and pasting code, stop. Turn it into a reusable function or class. Next, kiss. Keep it simple. This is a powerful reminder to just fight the urge to build something super complex when a simple solution will do. Don't over-engineer. And finally, Yagni. You aren't going to need it. This is all about discipline. Don't build features just because you think you might need them someday. Only build what you need right now.
So, as we wrap this up, I want to leave you with this one question to think about. Go take an honest look at your own code, at your current project. Is it a fragile house of cards, one wrong move away from collapse? Or are you applying these principles to build a solid, magnificent skyscraper that's truly built to last? The choice and the power is in your hands. Thanks for tuning in.